Hi everyone, welcome back to our channel. Today we're going to talk about the law of sines and law of cosines and when we can use them. And we're also going to do the proof for the law of sines. We're not going to do the proof for the law of cosines just for sake of time. It's a bit of a cumbersome proof. But if you are curious, I'm going to link the Khan Academy video so that you can check that out too if you want to see it. So far in trig, we've been talking a lot about right triangle trig and how to find different angles and side lengths for right triangles, but obviously most triangles are not necessarily right triangles, especially if you have a triangle created by things in real life. It's probably not going to be a perfectly right triangle. So we need to find ways that we can relate other angles and side lengths within triangles that are not right triangles. So that's where the law of sines and cosines are going to come in. So first, we're going to talk about the law of sines. So this is a triangle. It's not a right triangle. I didn't draw it to look like a right triangle, but also if your triangle doesn't have a little square in the corner of one of the angles, you cannot assume it's a right triangle, even if it looks like it might be. When we're labeling our triangles for law of sines and cosines, and generally in triangles, but especially for these equations, and how you'll see it most often, your angles are going to have capital letters, often A, B, and C, for angle A, angle B, angle C. And then the corresponding side length, or the side that's across from an angle, is going to be labeled with the same letter, but lowercase. So this is going to be side length A, because it's across from angle A, but a little a, and then side length B and side length C. So, I have this triangle. It's not a right triangle, so I can't just do sine of A is something, because I don't have a hypotenuse, I don't have any of that stuff. But what I'm going to do, in order to use my knowledge of right triangle trig in this triangle, I'm going to create a right triangle. I'm actually going to create two right triangles. So I'm going to cut this not necessarily down the middle. These are not going to be necessarily the same triangle, because I don't know if this is an isosceles triangle. I don't have that information. I don't know what these are yet. But basically I'm drawing a height, an altitude of my triangle that's going from one point to somewhere on the other side, and creating two right angles with this bottom side. So I have a right triangle on this side and a right triangle on this side. I'm going to call this height H. Okay? So now I have two right triangles that I can relate. So now I can say that, let's say, right over here, sine of angle A is H over C, opposite over hypotenuse. I can also say that sine of angle C is H over A, opposite over hypotenuse of that right triangle. Okay, so I haven't really talked about angle B yet, and we'll come back to that in a second. But so now I have an H in both of these. So how can I relate my sides and my angles of my triangle without the height in the middle, with just using the stuff from my triangle that's not a right triangle? Well, I can isolate H in both and then set them equal to each other. So I can multiply by A on both sides, multiply by C on both sides in this top one, and then I'll have, over here, I have side length C times the sine of angle A equals H, and I have side length A times the sine of angle C equals H. Now I can set them equal to each other and say that C sine A equals A sine C. And I can actually divide by A, divide by A, and divide by C, divide by C. And I'll get sine of A over side length A is equal to the ratio of sine of angle C over side length C. So sine of A over A equals sine of C over C. And this is actually going to also be equal to sine of B over B. And I wrote it, instead of just leaving it as C times sine A equals A times sine C, I divided it this way so that we can always see that the sine of an angle divided by its corresponding side length, they go together, A and A go together, C and C go together. That ratio will always be equal to a sine of the opposite of a different angle in your triangle divided by its opposite side length. So if I want to include B, I just have to draw a different height. I have to have my height going the other way. Or I could have drawn it from angle A, it doesn't matter. This blue height, I don't necessarily know. I don't know if it's the same height as my original H, so I'm going to call it a different letter. I'm going to call it, I'll call it X. So, but I can do the same thing and say, okay, sine of B is going to be X over A, and sine of A is going to be X over B. And I can do the same thing, solve for X in both of them, set them equal to each other. I'll end up with A sine B equals B sine A, right? And then I can divide again, and I'll get sine of B over B equals sine, oops, that should be a capital A, of A over A. And I know that sine of A is equal to, sine of A over A is equal to sine of C over C. And then I just showed that sine of B over B is equal to sine of A over A, which means by the transitive property, that sine of B over B has to be equal to sine of C over C as well. So all three of them will be equal to each other. The law of sines is that sine of A over A equals sine of B over B equals sine of C over C, where capital A, B, and C are the three angles within our triangle. Any triangle, doesn't have to be a right triangle. And lowercase a, b, and c are their corresponding side lengths, where a is the side length across from angle A, and so on. So this means that if you have a pair, if you have an angle and the side length across from it, and any other piece of information, so any other angle, any other side length, you can find the rest of the triangle. But you have to have at least one pair. What happens if we don't have a pair? If we have a triangle, and all we have is either the three side lengths, or we have what some like to call as SAS, or we have a side length, an angle, and then a side length, but not any corresponding pair that we can use law of sines for. So like if we have, let's say, 10, I don't know, 38 degrees and 12. We don't have a pair, and we don't have two angles, so we can't find the third angle to like create a pair, right? So we can't use law of sines for this. We also don't know it's a right triangle, so we can't use other right triangle trig. This is where law of cosines comes in. Again, I'm not going to do the whole proof, but I'm going to link the Khan Academy video if you want to check out that proof for funsies. But so, again, I'm going to label my triangle. So I'm going to label this as angle A, angle B, angle C. Labeling them is really important. It's arbitrary which one's which. You can call them whatever you want, but it is really good to help to label them and then to keep track of which one you labeled as which, right? Because depending on what information you have, it will impact what law of cosines you're going to do. There's going to be three different versions. So if I'm looking for, this is angle A, so if I have angle A, then I'm going to first try to find side length A. This is what I'm going to be looking for as my first step. And then once I find that, I can use law of sines to find the rest of the triangle, because I'll have a pair. So for law of cosines, we have a squared, side length a, lowercase a squared equals b squared plus c squared. So this side length squared plus this side length squared minus 2bc cosine of a. So it's a little bit long. But I have this side squared, like the other side length squared, plus the other side length squared, minus 2 times this side length times this side length, all times the cosine of the angle that I'm talking about. So for example, if I wanted to do it for a different angle on my triangle, I could have b squared equals, so like this side length squared would be the other two, a squared plus c squared minus 2ac, so the ones that I'm not interested in for now, times cosine of angle b. So the side length that you're solving for and the angle that you're taking the cosine of will always match. And then all the other things are going to be everything else. So like if I'm solving for b is only going to be in the cosine of that angle, and then all the other stuff will be the side lengths that in theory you know. And then the third one is obviously side length c squared equals a squared plus b squared minus 2ab times cosine of c. You can also use the law of cosines to solve a triangle if you only have the side lengths, if you don't have any of the angles, which is pretty cool. So you can solve for the angle that you would need in order for that triangle to be possible with a given 3 side lengths. So, try solving this triangle. Eight, 9, 10. Just made it up. The numbers might not be too pretty. You'll need a calculator for sure. But try solving this triangle. So find all 3 angles that go in this triangle. Again, labeling them to start will be really helpful so you can keep track of which one is across from which. And you can do it in degrees or radians, just make sure you're consistent. Okay, so I decided to solve for the angle across from the side with side length 10 first. I just labeled them A, B, C. So this for me is angle B. It might be different if you labeled it differently, but that's okay. So my first step, I just plugged in all the numbers that I know, so all my side lengths, and the thing that I'm solving for is the angle B that's inside my cosine. So I just squared everything, moved everything to the left-hand side, divided by 144, or negative 144. Now I have cosine B by itself equals negative 0.3125. I'm going to do this in degrees. I know I always do everything in radians, but for the sake of this problem and having things add up to 180 degrees, I just think that's nicer, or like maybe easier to see than having things add up to pi. But I'm going to put my calculator in degree mode, just mode, which is next to the second button, the blue button, down a couple. I'm going to hit over to degree, hit enter, so I can quit to get out of it. And now I'm going to do inverse cosine. So I'm trying to solve for the angle, so I need to do inverse. Inverse cosine of this whole thing, of negative 0.3125. Enter, and again, I'm in degree mode, so it's going to give me the answer in degrees, and I got that B equals 108 I'll round it to 21 degrees. It's like 2099, but make it 21. So I have that, 108.21 degrees. Cool. So now I can do law of sines for the rest of it. I actually only need to do law of sines one more time, and then I can just add them all up to 180 to get the third one. So I set up my law of sines. I don't need the third one because I only really need to find one more angle. So I decided to try to find angle A, but I could have found angle C. Same, doesn't matter. But so I have sine of B over B, sine of angle B over B is equal to sine of A over side length A. So I have sine of the angle I just found using law of cosine, sine of 108.21 degrees over 10, its corresponding side length, is going to equal the sine of angle A over 9, its corresponding side length. So now I just have to solve for A. And I'm just going to do that mostly in my calculator. So I'm going to do sine of 108, again, make sure I'm in degree mode, sine of 108.21 degrees, close parentheses, I got 0.9499, I'm going to divide that by 10, I got 0.09499, I'm going to multiply that by 9, because I'm going to be multiplying by 9 on both sides to get rid of the 9 in the denominator over there. So now this whole thing is going to be equal to 0.8549257719, and that equals sine of A. And now I'm going to use inverse sine of this to solve for A. So inverse sine of, I'm just going to hit answer because it's my most recent answer, and I want to keep all those numbers so I don't have any rounding issues, equals A. So I did inverse sine of answer equals A, and A equals 58.75 degrees. Cool. So now I just can add up my two angles in the middle and find my third one by subtracting from 180. So I have my last one, 58.75 plus 108.21, and then that's 166.96, so 180 minus that answer. This angle is going to be 13.04 degrees. Skinny. So now I've solved the triangle. I have all three sides and all three angles using both the law of cosines and the law of sines.